Module 8.3 Practical Applications of UQ. So, although we learned about a lot of mathematical methodologies, probability theory, and so on, it could look very daunting, but in this module, we'll learn using UQ is actually not that difficult in a way. So let's start with a very simple example of estimating the value of pi. So the value of pi is basically we are trying to generate random points in here, like using the numpy or random.uniform functions, and you can have how many number of points you want to generate using this variable n points. And now you can check whether this point on a plane, which is x and y coordinates, are lying within the equation of a circle, that is x squared plus y squared less equals to 1. You can count them. And you can estimate the value of pi by simpling just the number of points inside the circle and the actual number of points. And that's how we can estimate the value of pi. Now, if we use different number of sampling points, 10 versus 100 versus 1,000 versus a million versus a billion, you will see that as we increase the number of points, we'll get better and better value of pi. That's an example how different number of sampling could lead to better model or better predictions. And you will also have uncertainty in the estimate rather than having a single value. Now, we'll talk about a Gaussian process regressions. So when we are doing the machine learning module in the previous one to estimate the value of Steele's fatigue given the material input parameters, we developed several models using linear regression, random forest, gradient boosting, decision trees, as well as neural networks. So instead, if we use from the same scikit-learn package, the Gaussian process regressor, you'll not only get the actual input-output relationship that is predicting the value, but you also get the uncertainty estimate. Why? Because we are using something called kernel functions. And there are different type of kernel or covariance functions, such as the radial basis functions, Mattern functions, rational quadratic, and exponential sine squared kernel. So here we are trying to have a visual representation of, suppose you have a range of input from 0 to 10 with a 100 interval, for example, and we can sample the y value using the Gaussian process regressor and plot it on the right-hand side and see how these three samples look like under different kernels. So usually RBF is a very popular kernel technique, but you can also have constant kernel, of course, the C value, which is takes a constant kernel within an initial value and the bounds, or you can have RBF kernel with an initial length and the bounds between, for example, 10 to the minus 4 to 10, and so on. So maybe one of the exercises could be to analyze the effect of different kernel types on predictions of the Gaussian processes. Now, for actual Gaussian processes, let's assume we have a measurement from experiments and we know the ground truth. So as fx equals x sine x, that is our function. Suppose we know that in a one-dimensional case. Now, know that we are assuming that we know the ground truth function, but most of the time in real world scenarios, we do not really know what is the ground truth function is. So here, what we'll do is we'll plot this function x np sine x for a grid of value between 0 to 10. And it's shown on the right hand side in this function fx x sine x. Now, suppose we have 6 measurements. Now you can have multiple measurements, but suppose we measure at 6 points in that curve, randomly selected, and we will have that x and y value. So x is the value on the x-axis and y is the point on that x sine x function. And we will use RBF kernel and on the right you can see below, and we'll try to develop a surrogate model or Gaussian process regression model with the dot fit function. So has taken X trend and Y trend, and now we have a regressor model. Now we can make predictions on the entire X, which is the total grid. And you can see that the points which the Gaussian process regressor has already seen, the uncertainty, which is the orange envelope, the uncertainties are very, very low, while the points which it had not seen, the uncertainties are very, very high. So it will tell you basically where to do the next measurement. So if the measurements on the left-hand side, suppose between 0 to 2 is very high, so it will suggest you to do the measurement there instead of between 4 and 6, where the uncertainties are very, very low. So in this way, the uncertainty estimate can help choose the next measurement, for example, instead of doing brute force like sampling for all of them, all the points on the x-axis. And yeah, we are predicting the mean predictions. We are predicting the 95% confidence interval. And this is a very simple but very powerful example how to use Gaussian process to get uncertainty estimate to guide us what should be the next step in a experimental measurement or also in modeling techniques. Similar technique is the quantile regression. Especially, we'll be using here the California housing data set. And you can take the housing data set from scikit-learn, and it will give you the X tabular data and Y tabular data. You can do a train test split, which we did in the previous machine learning module. And we'll use something called LightGBM, which is very similar to the scikit-learn gradient boosting decision tree model. And we will develop three models, one for the mean model, one for the alpha equals to 0.05 model, and upper, which is give you lower prediction, and the upper bound, which is the alpha 0.95. So here, instead of having only one value, which is a red, we'll also have the upper and lower bound, which is plotted here. So in this way, now if you have these three models, which is the regressor, the lower and the upper bound, and if you have a new sample point, you'll get three values instead of just one value. And you can see very similar to the Gaussian process example, what is the level of interval? Is the interval very low or very high? And based on that, you can do the next sampling point in your measurement.